Okay, everyone. Good evening to all. I am Shiv Prakash, Research Scholar, Department of Electrical Engineering, IIT Virtu. I am here to take your live session regarding to your assignment and numerical session with course of Fundamental of Power Electronics and taught by Professor Lumanan sir, Division of Electrical Electronics and Computer Science, IIC Bengaluru. I am take only your assignment session. Question related to the assignment you can solve easily by taking this class. Okay, let us start the session. Let the given question number first. Piecewise linear EV characteristic of the diode is shown in figure. The cut-in voltage of diode. I think all of you are solved already this question, but we should know about the piecewise linear characteristic. Piecewise linear means some part of the characteristic is linear. We will see like that. This one. So it's like a linear characteristic. And you know about the diode IV characteristic like that. Voltage, this one current. I think this one a practical diode. This is voltage of forward voltage drop, and this voltage blocking voltage capability of any diode. And you know as normal diodes, silicon diodes. This one I think 0.7 volt, and this one for silicon material, and 0.3 volt is for germanium. Reverse blocking capability is this one is a different for different part number of diodes. If you made for the high voltage blocking capability, this one is higher, and if you want to manufacture for the low voltage blocking capability, then it will depend on the manufacturing blocking voltage capability. Many type of diodes has a blocking capability is very high, and some diode is very less, and this such as a PN junction diode. And this one is dependent on the material you used and which for which purpose you used for blocking capability. It depends on the manufacturing. I think this one 5 volt, 10 volt, 100 volt, and 200 volt, 500 volt, and 1000 volt also. It depends on the manufacturing. And this one is the leakage current. You see here, this one leakage current. This one in microampere. Reverse in the reverse direction. That's okay. You know about the linear characteristic like that. This one of any diode. This one an ideal diode. Reverse blocking capability, voltage blocking capability is infinite. You can't flow the current in reverse direction in ideal cases. In practical cases, this one is the maximum current flow. Its blocking capability, forward blocking voltage is 0 for the ideal cases, but it is not possible in practical. Practical is like something, this one characteristic. This one not a pure linear characteristic. If you observe this one, you find some of the point is linear, like that, where you use a diode. This one is called like a piecewise linear. This one is a piecewise linear, like that. Some here linear. Also, if you zoom there, here we find the linear. This one is the piecewise linear characteristic. Here is given a piecewise linear characteristic of a diode, and he asked about the cut-in voltage. Cut-in voltage is forward blocking voltage. Which voltage is given from forward direction, then diode will on. Okay. Now it's okay to everyone?
Yes, sir.
Okay, thank you. Dhananjay Devkar,
Yes,
please,
sir.
please off your mic.
Yes.
Here ask about the cut-in voltage. It means forward voltage. Yeah, you see in the characteristic, this one is the forward voltage, block cut-in voltage. Then I think approximately 5 volt, 0.5 volt. This one 0.4 volt is 0.1 volt per square section. So 0.5 volt the cut-in voltage of this diode. Okay, let's second question. Tell the question number first, the dynamic resistance of the diode. Dynamic resistance, it means slope of the diode, of the characteristic. This one is slope, I think current and voltage. You know about the slope. This one delta V changes, in this one delta current I. Dynamic resistance means delta V, delta I. If you take any, you can take anywhere the linear characteristic. If you take like this one at the 0.1 voltage, 0.1 volt, then this one the current. You take this triangle, I think 0.3 ampere, means R 0.33 ohm. The dynamic resistance of the diode of this characteristic. So also known as the load curve of the diode. Okay. This one R 0.33 ohm. Question number third, unit of thermal resistance. Thermal resistance, you can see here. Thermal resistance means the difficulty how to flow up heat from one point to another point of any material. Like it is dependent on the material. If you choose a different type of material, the heat flow is different. Such as like current. If you take a high resistance, it means yes, double radii. You want to say something? Same as you know about the current flow V1 minus V2, it means if voltage difference of any point in a circuit, there is a flow of a current. Same as like a thermal resistance, if you put temperature difference between the 2 points, the heat is flow. Yes, yes. Heat flow, you know about the heat. Heat is, it means energy, contain of energy, it is. And the heat flow means rate of change of energy, it will power. You know power into T is energy. If you differentiate energy, you find a power. It means heat flow means power flow. If a temperature difference between 2 points, the power flow from one point to another point. Depend it. Then RTH to thermal resistance, like a T1 minus T2 difference between 2 points. Then you say that temperature is in degree centigrade. For heat flow means what, and what also you can change what unit in the joule per second. Joule is an energy unit, and joule per second is the watt, a power unit. Like this one, you can change also degree centigrade in Kelvin. In Kelvin per watt means joule per second. Option C is correct. Thermal resistance, it means a temperature difference between 2 points divided by heat flow. Heat flow occurs, it will depend on the thermal resistance of the material, of any material, same as Ohm's law. The whole idea, you want to say something?
Yes, sir. Am I audible?
Yeah.
Sir, I was watching lecture of Sir L. Anand. Sir was saying that it should be either degree Celsius per watt or degree Kelvin per watt. Or
Yeah.
but you can either write as a degree Celsius per joule, which is the
No,
first option.
this is not. This was degree or degree centigrade per joule. Joule is not a joule. Joule. This is power. This is energy unit, not a power unit of joule. Joule, but your thermal resistance degree centigrade per watt, not a joule. If you change the watt into joule in energy form, then you find a joule per second energy. This one is the watt.
Mhm. Okay, but sir, it will come degree Kelvin, right, sir, or not?
Yeah. You can degree or degree centigrade or Kelvin. You can change it. Don't worry. Don't
Okay, sir. Okay.
confuse of them. But here is the different on joule and watt. That both are
Hmm.
different units. Joule is the energy units, and watt is the power unit.
Power. Okay. Thank you, sir.
Okay, welcome. Yeah, I think it's a little completed. Yeah, circuit diode. Question number 4. A circuit diode carrying a current of 5 ampere with a forward voltage drop of 0.5 volt is used in a power converter. If the diode has junction to ambient thermal resistance 40 degrees centigrade per watt and operating at ambient temperature TA as a 40 degrees centigrade, calculate the junction temperature according to only the conduction loss. Conduction loss is they are given here. Schottky diode is given 5 ampere forward current and forward voltage. This one voltage. This one given is 0.5 volt. You know about the Schottky diode. Schottky diode is a very fast diode. As a reverse recovery current is very fast. You find the first one, you find a power. Power is 5 into current to voltage. Average current to average voltage 2.5 watt. Here given the thermal resistance. First one, you know about the step of thermal resistance. With this one a junction, then this one a case, this one for the sink, it's this one ambient is the outside of the temperature, this one ambient temperature. In every step there are the thermal resistance between here, as you can say RJC. Theta also represents the thermal resistance, like theta, then theta CS, case to sink, this one theta sink to the ambient. There's some more question asked about the average power. So when the diode is subject to the sinusoidal voltage, then it is average power to be taken. Okay. I explained. I will explain further. Don't worry about that. Where you use the average quantity, where you use the RMS quantity of any signal, sinusoidal signal, square wave signal, DC signal. Which one you applied? I explain further. Don't worry. In next question, I think. Explain first question. So this one, piecewise linear. Piecewise linear means of any characteristic, diode characteristic. If you see in characteristic table of any diode in part wise data sheet, then you find like that if any diode of a practical diode. This is not the ideal diode. In practical diode, not the linear characteristic. You can't find the linear characteristic in practical diode. In such a characteristic, you find a piecewise linear. We study the piecewise like that. This one, you take this one like another, this one a linear, this one says like a piecewise linear. Here represented the piecewise linear characteristic. In linear characteristics, you find the resistance, dynamic resistance, you find easily. But if you have a non-linear characteristic, then the resistance will be different of them. You can't find easily. That's why we will choose as a piecewise linear characteristic of any diode or any switches also. And in first question, you ask about the cut-in voltage. Cut-in voltage, what is the voltage where diode is on? This one I think cut-in voltage. If you see here, this one 0.1 volt per square column, 0.4, this one is 0.5 voltage answer. The second question asks about the resistance. Second question also find a dynamic resistance. Dynamic resistance means changing the voltage by changing the current. Change the current by the changing the voltage, the resistance of any devices, and then you can choose any of the point here. If you choose one square column, you take 0.1 volt, and what is the current from here to here, you find like a 0.3 ampere current, and you apply 0.1 volt after the cut-in voltage. Then you find delta V is 0.1 volt, delta I is 0.3 volt, or 0.33 ohm. Okay. And here the circuit diode carrying a current of 5 ampere. You find the power. Power is the same in thermal and electrical. You can use a power. Here you ask about the R junction to ambient. It means this one is given totally, or all of the resistance, thermal resistance. The power flow means this one junction, and if you have a ambient temperature, then it is written like that: junction temperature minus ambient temperature divided by resistance of a junction to ambient is equal to power. This one power is given like a 2.5 watt. TJ junction temperature also given. Sorry, this junction temperature is asking about. Then TJ P into RTH to J plus ambient temperature 2.5 2.5 into RTH given 40 degrees centigrade per watt plus TA is 40 degrees centigrade. 140 degrees centigrade temperature of the junction. We also verify the junction temperature is high always to the ambient or any other. This one junction temperature is always high and reduces the case temperature less than the sink. So this case temperature is greater than the sink and sink greater than the ambient temperature. Junction where they place the devices have a junction temperature, PN junction temperature here, and case where the amount of the devices and sink provide for the cooling, and ampere is the overall the boundary of the devices, the outside of the devices, the ambient temperature. Question number 5. Referring to question number 4, the junction temperature calculator for write like a power 2.5 watt is the same. The junction temperature calculated is outside the maximum operating range of the diode is 120 degree. It is given the diode or any devices have a maximum temperature, operating temperature. You can't operate beyond 120 degrees centigrade. You have always less than this you can use. Calculate the thermal resistance of heat sink to ambient. Same as this one junction, this one case, this one sink, sorry, junction, case, sink, ambient. Heat sink to ambient is required. You calculate thermal resistance of the heat sink to ambient. This one sink to ambient, RTH, SA, required for the junction temperature TJ to operate at the 100 degree centigrade. It means the Tj is given as a 100 centigrade. The maximum operating temperature is 120 degree centigrade, but you say about the junction required junction temperature is what is the thermal resistance is required for the junction temperature maximum operating 100 degree centigrade, and our Th junction to case, this one is also given. (10 degree centigrade per watt), and RTH CS means this one is given 3 degree centigrade per watt. Same formula you can apply. P is equal to all of thing. Tj is given Ta ambient temperature, things are not given, and then ambient temperature using ambient temperature, I think Ra given. Ambient temperature same is given here, 40 degree. Take there, and P is equal to 100 degree centigrade minus ambient is 40 degree centigrade divided by all of the thermal resistance, RTH JC plus RTH CS plus RTH SA. (2.5) can also be written like that, RTH JC plus RTH CS plus RTH SA is equal to 60 divided by 2.5. Is asked about the surface to ambient temperature resistance 24 minus JC 10 minus 3, that is on 11 degree centigrade per watt. Surface to ambient temperature you have required 11 degree centigrade per watt. 11 degree centigrade, it means the thermal resistance to flow up any heat. So then data of the outside max temperature 120 degree. Yeah, this is given for the safety purpose. The maximum operating temperature of diode is 120 degree, but he say like the 100 degree you can use for the numerical is given 100 degree it will use. It has used, it has not used the 120 degree full of the range of the any operating diode, operating range of the diode. This one given as the maximum operating range of any diode, but he operate the diode to 100 degree centigrade only, not 120 degree centigrade. That's why you take only 100 degree centigrade. Next question is given, on the piecewise model of a diode, we get dynamic resistance of the diode is 50 milliohm. The knee voltage of Vd is 0.6 volt. Once the knee voltage of cutoff voltage, you can say same like that. This is given a piecewise linear. This one voltage 0.6 volt. Resistance is given 50 milliohm. Diode connected in a series with a 40 volt square wave voltage source 0 to P. Voltage like this one. 40 volt, 0 volt, and 20 ohm resistance. So you draw a circuit like that. This one VDC. So diode is on RL circuit. Diode replaced by the resistance in on condition plus minus a voltage. This one RDS on, RD, and VD is a diode cutoff voltage, a forward voltage. This was a symbol of diode. If you this one on off on condition, it replaces this one RD and VD. But it is asked about the forward voltage drop across the diode. It means total voltage drop. The voltage drop found by the current I into RD plus VD. If you find the I current plus the forward voltage V by RL, (40) 2 ampere, then forward voltage is I into 2 into RD. RD is given 50 milliohm plus 0.6 volt. VAB 0.7 volt. This one is prox value because of some resistance and voltage drop also. If you want to find exact value of this, exact value of a VD, then you find like a closed circuit. You replace up the diode by this one. Okay, I will discuss. In on condition, if you see like this one, this is the VS. Yeah, duty cycle is not mentioned here, but it's asking about the forward voltage drop, not the average forward voltage. Forward voltage, which when a switch, when a diode is on, then what is the forward voltage? If a duty ratio is given, then you find the average forward voltage. But here is not asking about the average forward voltage. It is simply asking about the forward voltage. When you apply the voltage, some voltage, 40 volt apply, then what is the forward voltage drop?
Sir,
Yeah.
uh, to be more accurate, shall we consider the forward drop of the diode, that is 40 minus point
Yeah, I explained.
volt.
I explained.
40 minus 0.6 divided by
Yeah,
20. and that
20
will be the current.
resistance. No, resistance also divided by resistance. Yeah,
Divided by
yeah, I explain.
and that 20 plus that resistance will
Yeah,
be that current, and then this current will have the drop across the diode RD, and then we have to get the total drop.
I explain it. This one I'm saying like this one is approximate, not exact
This
value.
0.7 is approximate, but I think
If you calculate exact value, then you find
it will come somewhere around 0.65 and 0.7
things
in between, like.
yeah.
So we have to calculate it that way, I think so.
Yeah. This one I'm saying this one is approximate value, not exact value. Exact
Not
value
exact.
I will calculate exact value. Don't worry. If you want the exact value, then you should conclude the RD and VD also.
Yes.
Yeah. Then first to find the current. Current is
Yes.
this one voltage minus this one voltage.
Uh,
This one of 40 minus 0.6 volt
mm,
divided by RL plus RD.
mm.
Then find the current from here, and after that to find the forward voltage like I into RD plus VD is the exact value of I think 0.695 something.
695.
Yeah, I think this you calculate once what is the exact value. The approx 7 volt, 0.7 volt, not exact 0.7 volt. Okay.
Okay.
Question number 7, from the piecewise model of a diode, you get a dynamic resistance of a diode is 50 ohm, milliohm, same I think. New voltage 0.6 volt, and this diode is connected in series with a 40 volt square wave voltage source. D2 ratio also given here, and 20 ohm resistance. I think same resistance also. The on state power loss of the diode. Here you say like a power, and this one diode is one current R plus minus is I think VD, and ask about the power loss, total power loss of the diode. Okay, you know about the power. Power is a 1 by T, 0 is time period, 0 is T, Vi into V into I into dt. This is the power, actual power of the any devices. Here is the I think 3 cases I will take here. This one resistance, and what if you have a voltage, and what is when you have both. This one. First of all, I take a current or voltage. You can also apply here a resistance. Then power, you calculate power 1 by T integration of V into I into dt, 1 by T. V voltage means I into R. I take a small value of notation of the current. Then I into R, the voltage into I of the current. Then 1 by T integration of I square into R into dt, and 1 by T integration of I square into dt into R. And I am written 1 by T integration of I square into dt. You know about this thing, RMS value. You find the RMS value of any waveform, IRMS, voltage RMS. You know about the root means square 1 by t integration of some current square into dt. This one the RMS value of anything. You can square of this, then RMS square is equal to 1 by t integration of I square into dt. Same as this one. Then you say about the power, you say P is equal to I RMS square into R. It means you have a diode and current passing through a diode, then power of power losses of in this diode is I RMS square into R, not I R average, I R peak or something. You can find a RMS value, after that you find power loss. Yes? Someone want to say?
Hello.
Yeah.
So can we take that V squared upon R also, no? V squared RMS.
Yeah. You can also
So
say.
we have already calculated V, that is 0.7.
No, this one
That is
not
across the diode. Okay.
Yeah, this one not average value. Yeah, this
Not
is
average.
mention. This is not mention average RMS value. Then you can't
No, that is not
take
average.
directly
Okay.
0.7 volt.
But 0.7 volt into root of that duty cycle, root of D of V of diode will
Yeah.
give the RMS of that diode.
Yeah, this type of you can take this.
है ना?
Yeah.
Then it will come. That is the root of 0.5 into 0.7 bracket square divided by R. I think so.
Yeah, this one you can take, but you cannot take it directly as a voltage.
No, not direct.
Yeah, you can take a RMS. Same thing, you apply the voltage here, but you say like a 0.7 volt and overall voltage, not resistance across the resistance.
Not across.
Yeah, this one overall voltage 0.7 volt.
0.7.
Not across
Okay.
the resistance voltage.
Not resistance.
You can't say like the same voltage apply in the resistance.
Yes.
First find a current, cross current, and take RMS value of the current, and then find the power loss of the. Okay, same thing you apply a voltage waveform, then simply and replace the voltage the current by the voltage. I can say written here 1 by t integration of, in place of current is V by R, then it is V square by R into dt, then 1 by t integration of V square into dt into 1 by R. This one is the voltage RMS. It means if you apply a voltage current across the resistance, then you find the RMS value of RMS value of current or voltage, then you find the power losses of the actual power loss of the resistance, because the resistance. Same thing here. I think what happened if you have a voltage only. A voltage source. Yeah. Some voltage like a VD or some other voltage. If you have a current waveform of any waveform, it can sinusoidal, it can square wave, it can triangular, anything. Then you find the power. Power is the same formula, V into I into dt. Here VD is a constant voltage drop. Then voltage is same, VD replace and I into dt, 1 by t integration VD a constant, take outside of this into dt, With this value of 1 by t integration of any quantity, this area under the curve is the average value. It is not RMS, this is an average value. Then you can say here I average into Vd is the power law. It means you have a voltage source, some voltage source, and the current passing through the source. And then actual power loss of the this power source is the I average into voltage drop. It is not the RMS value or not a peak value anything. It's an average value. Then here resistance and voltage drop both are present in diode. And if you have calculate to the actual power loss of a diode, you calculate the RMS and average both of the waveform. Hello. Someone I think disturbing this. Please don't do this like that, this type of thing. I think anyone by mistakenly click on the share button. Prudvi Raju, Prudvi Raju, I think. Please don't do this thing again, please. Here I am. I am find the power loss of the diode. Total power loss means both are presented, resistance and voltage drop also. And first of all, find the average and RMS value of a square wave is given here. I am writing directly average of the square wave (40 to 0.5 to 20 volt) and RMS 40 divided by root 2 you can also take title root 2 divided by 2 10. Sorry. Please calculate this. I think this one 28 point something will 28.2 the RMS value. I am find current directly. I approximate the value. Voltage given 40 volt square wave. Find V average 20 volt, V RMS 28.28 volt. Average you find V average by RL 1 ampere. IRMS V RMS divided by RL 1.4 something for 2 ampere. Power loss IRMS square into RL plus I average into VD. Yeah. Dhaval ready. You want to say something?
Yes, sir. Actually, I have solved this. I think I know I'm wrong, but I have taken, sir. I average means we know that I average will be equal to 0.637 into I maximum current. Okay. So using that formula, I have taken as I average as a 2. So it is. Can I take a average value as a 2 amperes as is given question?
I average not given question.
So um,
Is given a 40 volt.
40 volt.
40
Okay, sir.
voltage square voltage. Then
Okay.
you find the average voltage of square wave. I think duty ratio also given 0.5. It's half of the voltage. 20 volt is the average voltage. After you find the current.
Okay. Yes, sir. No, I have what I've calculated. I have given V by R. I have done I is equals to V by R.
Yeah.
So directly 40 by 20. So I
2
got 2
ampere.
amperes.
Yeah. After that you find the average current and multiply by 0.5 duty ratio.
So, sir, that 2 ampere current is what current means if it is not average? So, is this peak current?
Yeah.
That 2 ampere.
Peak to peak current like this one. I explain. This one is the voltage. You have voltage. Okay.
Yes, sir.
0 to 40 volt. This one voltage we have found.
Mhm.
0.5 T and duty test T. The same thing of you have current. If you directly apply this here, then you find a current we found same as. And this one is a V by R. Okay.
Okay, sir. Okay, sir. Now I got. I have not considered the duty cycle. Okay.
Okay.
Thank you. Thank you.
Okay. Welcome. After that, you find a I average and IRMS from these you found. Then you find I average 1 ampere and IRMS 1.42 ampere. Then calculate the overall power. IRMS. So this one RD. I think 0.7 watt something. You calculate this one. Sorry. Okay, everyone. You have some confusion about this one?
No, sir.
Okay.
Sir, what is the last equation?
Yeah,
Yeah. Last equation. I RMS square into P is equal to I RMS square into, sir.
I RMS into I RD,
Okay.
diode resistance.
Okay.
It will give an, I think, 50 milliohm.
Okay.
Yeah. When you have a resistance, then you find a RMS current, and you have a voltage source, then you find a average current for the power calculation.
Perfect.
I will also upload this video on the YouTube. You can watch there after closing the session. And
It will be definitely helpful, sir.
yeah,
It will be definitely helpful.
yeah. I will upload this video on the YouTube also. Don't worry. And the link I think is shared by you in NPTEL website. Okay, question number 8 is given here. Feature of the ideal switches. I think all of you know about the ideal switches.
All of above.
Sir, excuse me, sir.
Yeah.
Sir, that P equal to total power loss in the circuit, sir.
P.
That P.
No. It one is the power loss on diode only, not a circuit, total circuit. Power loss for the diode.
Okay, sir. Okay. I got, sir.
Yeah.
VD is the voltage of, yeah.
Yeah, some voltage drop on the diode. Forward voltage you can see, forward voltage drop, or knee voltage or cut off voltage of diode.
Yeah.
Okay.
I got, sir. I got the point.
Okay.
Yes, sir.
Feature of an ideal switches. I think all of you know about the ideal switches. No resistance, and then reverse bias the infinity resistance. This one IV characteristic of any switches.
Hello.
Yeah.
Hello, sir. I have a doubt actually.
Yeah.
Can you comment on the time delay of the ideal switch?
Time delay 0, na?
Okay. It should be zero, right?
Yeah.
Okay.
This one is the ideal switches characteristic, IV characteristic. Forward bias, the current flow from a zero origin. You suddenly apply the voltage, the current will flow. And in critical cases, it will take forward voltage drop by some voltage, cut off voltage. After that, current flow. But in ideal switches, you current flow when apply a minimum voltage also. And then the reverse blocking capability is infinity. Infinity means you apply a higher voltage, infinity voltage also in for reverse bias, the diode is off state. It will not on anything. But in practical cases, it's not possible. In practical cases, switches have some clocking capability up to voltages, like if you know about the thyristor, they have a maximum voltage blocking capability. IGBT also have a maximum blocking capability. MOSFET some, I think they also 1000, 2000, and 2500, 30,000 also have a reverse blocking capability present in the market, and thyristor and IGBT have a enough to block the voltage, the higher voltage, I think kilovolt also, even kilovolt, more about that. And on resistance is 0. On resistance means 0 means it have a 0. This one is given as the diode as a dynamic resistance 50 milliohm, but in ideal switches it will be 0. It is not any resistance provided by the diode. And during the on condition, conduct infinite current in both the forward and reverse direction. It means you apply a voltage in any direction, you want to flow current, then it will this one infinite current in some voltage, not a forward voltage. This one, I think this one is apply some voltage and current will flow. And during off condition, you stand the infinite blocking voltage. Both all of it. So, yeah. You want to say something?
Sir, actually, yeah, sir. Actually, I have a doubt here again.
Yeah.
Like IV, the graph here, no, the IV graph, it is linear actually here. It is the signal is like ramping signal. Okay, sir. So
Yeah.
it will have a slope, right? So the dynamic resistance will come, right? Sir, yeah. But you just told the dynamic resistance will be 0 or something.
This one
Can you explain this
called
point?
load curve, but the dynamic resistance is 0.
Okay, but slope will come, right? The slope will indicate some change in resistance.
Sorry. This one not.
This should not be there.
Yeah.
It should be straight line.
This is straight line, not a linear case. Linear is different.
Understood. Understood. Yeah,
Yeah.
that diode I
Sorry.
understood, sir.
Sorry for that. This one is straight
Yeah,
line.
understood, sir. Okay.
Okay.
Ideal switch.
Yeah. Ideal switch also, if you have a current, and this one will voltage, this one on state, this one off state. When switch is on, the current is flow like that, and switch is off, the current is 0, voltage maximum voltage apply on the diode. This one duration of this one is 0, not any delay of current and voltage. In ideal cases, but it is not possible in the practical cases. Practical cases, I think some you know about this one now duration. This one off duration. This one on duration in practical cases. The current voltage waveform. Here the switching losses also find from the current and voltage switching condition. Here when switch is on and switch is off, some overlapping here. When switch is on, it means current is flow, voltage is 0. Then power loss is 0, V into I. Voltage is 0, it means power 0. And here when switch is off, power also 0. It means current is 0, voltage high and power 0. But in transition condition, voltage and current both are overlapping some point, this from here to here. Here is the switching losses there also. In switches, the diode have a, I think diode is only one directional switches. You have a MOSFET and IGBT. In this condition, you have a maximum losses on the switching losses like that. If you have a frequency of like 50 kilohertz, 100 kilohertz, 200 kilohertz, like that, then switching losses are high. In that condition, you should have a soft switching like this phenomena also. You can do this. Yeah. And Nagas, you want to say something? Okay. How infinite reverse current in on condition? Oh, so this one is switch, which one switches to bidirectional switches. It means the bidirectional switches during on condition. If you have bidirectional switches, that means the forward and reverse direction you have an infinite current. But if you have one directional switches, then it means current flow in one direction, not a both direction. It means if you apply in diode not possible. It is say about the switches, not a diode. Diode have only one direction, but the switches have a bidirectional also. Some switches have a bidirectional also. In that condition, the forward maximum current flow, infinite current flow in forward and reverse direction during the on condition. And when the switches is off, it means forward bracket voltage infinity. In case of a diode, it can be flow both directions. The reverse recovery time of a diode is 4 microseconds. What should be the peak reverse current approximate to recover the stored charge during the changeover from forward condition to the reverse blocking condition? Stored charge is 100 microcoulomb. Okay. We have a reverse recovery characteristic like that of any diode. This one a forward current, IF. This one a reverse current. Maximum current you can say IRM, reverse maximum current. This one time of reverse recovery, TRR. Then I think it will give in reverse recovery time of a diode 40 microseconds. And you can divide also here from TA and TB. We'll ask about the maximum peak maximum current. This one, peak reverse current, maximum reverse current, IRM. If you observe this circuit, it will give an approximate. Approximate means you can take as a triangle of this one. If you take a triangle of this one, then this one is the height of triangle, this one is the base of the triangle. Then we find the area under the curve. You know about the charge current, it flow like a dq by dt, and if you find a charge, then dq is equal to I into dt, integrate in both direction, both sided, integration of I into dt. This is the total charge. I into dt integration, which means area under the curve. Sorry, area under the current curve. Then you find easily the area of the triangle. Area under the triangle is the charge, the area of the curve. Find total charge Q. Area of the triangle is a half into base. Base is TRR into base into height. Height is IRM. Then you can find IRM. As total charge is given 100 microcoulomb into 10 to the power minus 6 into 2 divided by TRR. TRR given 4 microsecond. $50 ampere. It means you have a forward current, and when you off the diode, when you off, it means a reverse current flowing like a 50 ampere for the certain and some amount of time only, but 50 ampere is very huge current, I think. And next question is the final question, I think. Then ultra fast diode. Ultra fast diode, which means the reverse recovery time is less in any diode, but if is given ultra fast diode or circuit diode have a very less time of reverse recovery charge. And in the switching purpose, you used in I think you have in SMPS. You know about the SMPS, switch mode power supply, and you used a converter, buck converter, boost converter, buck boost converter, many type of converter. In that cases, you use the Schottky diode or ultra fast diode, because the reverse recovery time very less. Then the losses on this diode is very less, because of this one. TRR is very less of a reverse in Schottky diode and fast recovery diode. In normal diode is very high. 4 microsecond is the very high time. Ultra fast diode is given carry forward current of 50 ampere with a DIF by dt. It means the slope of the current, reverse recovery current, 100 ampere per microsecond. From the data sheet of the diode, find out the peak reverse current IRM during the diode is off. Same thing. This one time, this one current. On IF, on IRM. Then is it take a maximum current is defined by TA, and this one defined by TB, and this one is TRR, reverse recovery time. Given an ultra fast diode, I have a forward current of 50 ampere. This one given is a 50 ampere current. DII by dt, it means slope is given also 100 ampere. From the data sheet of diode, find the peak reverse current. You should know about the any devices like MOSFET, IGBT, diode, ICs. In each have a own data sheet or own port number. This one is the port number given. It will define in the data sheet what is the value of forward current, what is the value of reverse blocking voltage, what is the on resistance and drop voltage. Everything is given in the data sheet of any devices. And when you use some devices like MOSFET or diode, then you should know about the data sheet of that MOSFET devices. Then it's given a part number. Every switches and every ICs have a part number. And I think every resistance, capacitor, inductor have a own part number. Search from the Google. You can also search from the Google or URG5060. You find the data sheet of the diode. Which one diode is it? I say you the part number of the diode. This one the same diode. So given a part number, and all of information is given from of the diode. The 50 ampere current is forward current, and 600 volt is given in the. It means the reverse blocking voltage of diode. There is also given reverse voltage. This diode have a 600 volt reverse blocking voltage. After this one break down the voltage, break down diode and current flow in the reverse direction. It has a 600 volt in the reverse blocking capability.
काय नाही एक डाटा शीटचं आहे.
Yeah. And see here, recovery characteristic TRR less than 65 nanosecond. And previous diode you have a microsecond reverse recovery characteristic microsecond, and in fast ultra fast diode you have a less than 65 nanosecond. If you see about the Schottky diode, then there you see like a very less TRR. Reverse recovery time very less. I think 65 also less than the 65 and 45 or 40 nanosecond. Some lesser also present in the market. The information given about this. You see a diode. This diode like seen like this. This one is the cathode, anode. Cathode also here metal bottle. If you check in back side of the diode, there also cathode. And you Schottky diode, if you see Schottky diode, there are 3 pins, 2 pins for the cathode, 1 pin is the anode. But here is given this was an ultra fast diode, have 2 pins, and all information is given here. Peak repetitive reverse voltage is 100 volt, working peak reverse voltage so 600 volt, blocking voltage 600 volt, forward current depending on the temperature is given 1 or 2 degrees centigrade. Maximum temperature have a 50 ampere current. Repetitive peak surge current. It means what is the current you apply sudden apply. Like a surge current is a sudden apply. When you switches on, the huge current flow at that time. I think spike. Spike. If you switch on of some devices on off, and that time due to the some inductance, parasitic inductance, devices have a huge current, take a huge current, spike like a impulse signal. This one is given like a surge current. Surge current we take a 100 ampere, and non-repetitive surge current, peak current. Repetitive means some oscillatory, and non-repetitive is the certain 500 also you can apply, but some like in nanosecond or picosecond only. Maximum power is dissipation is 150 watts This is a very large power drop, power loss in the diode. 150 loss if you use in a full load like a 50 ampere current and 600 volts blocking capability. If you use switching frequency also have affected the power loss. Operating temperature minus 65 to 175 degrees centigrade. Here is given forward 1 ampere with 65 nanosecond, but if you increase the current then it will take a 75 also. But here you see like a TA and TB. TA is given in 50 ampere current 100 microsecond. Someone asked about the reference book. You can use a you can read yes, Bimra also for power electronics, and Elumanand sir have his own power electronics book. Yeah, for data sheet is given 30 nanosecond we solve get IRM 33 ampere is correct, because of the given 30 nanosecond of TA. TA is given 30 nanosecond, TB is given 20 nanosecond. RJC junction to case temperature also given, thermal resistance you 1 degree centigrade per watt. This one, and also from the characteristic you will find like a 10 ampere, 20 ampere, 30, 40, this one 50 ampere correct. This one is TA, this TB 20 nanosecond, this one is 30 nanosecond. If you increase the temperature, then average forwarding current will decrease. 100 degree centigrade is enough. 75 or 80 is the maximum operating temperature of any circuit. You can't use beyond of this 80 degree centigrade, 100 degree centigrade, very huge temperature. This one gives TA value. TA is given at 30 nanosecond. Okay, go to the question. So, this one given TA, find 30 nanosecond. Then you apply like this one, take as a slope of this one on to off. If you find a slope means in y IRM minus 0, this one is 0 current, divided by time taken from like this one is TA is the slope, and this will also be given DIF by dt is 100 ampere per microsecond. Then we find IRM, IRM is equal to 100 into TA. 100 per microsecond means 10 to the power minus 6, and TA is given 30 nanosecond and 10 to the power minus 9. Got to this one minus 3 ampere is the reverse recovery current, peak reverse current. Okay, and this one is the last question, 10 this. If you have some doubts, you can ask. And someone asked about the comment.
Sir, today you will discuss only about assignment number 1.
Yeah. In next
Sir, what's about
next week,
that?
Yeah.
Sir, what's about that assignment number 2? When you will discuss that?
And next week.
Next week. Okay.
After the due
Sir,
date.
one thing that after the due date.
Yeah. No. I think and assignment number 2 is not a due date. No. What is the due date of assignment number 2?
It is on 8th, sir.
Sir, both assignment 1 and
Before due date
same
only,
date,
sir.
sir.
February 6th, sir. It's before due date only.
Both are given to you. Both are given. Tell me a due date of the assignment 1st and 2nd, please.
February 8th. February 8th, sir.
8.
8 February 2nd.
Both, sir.
Oh.
Both, sir. One as well as that second one. Both, sir. Due date is 8th February, sir.
Okay. But I have discussed only one assignment number 1 only.
Sir, one thing, because in assignment I have to manually provide that answer, sir. Suppose one answer is 0.333. So after decimal, how many digit I will write, sir?
2 digit enough.
Only 2 digits, sir?
Yeah. 2 digit enough. 0.33 enough.
Sir, if I use more than that, will the system take the answer as a correct?
Yeah, you're correct. So you have provided a range of answers. Don't worry for 0.33. If you have an correct answer 0.3, you provide 0.25 to 0.35, like that.
Actually, sir, in assignment number 2, there are many questions where means after decimal, many number of digits are coming. So I confuse that how many digits shall I put there?
Provide 2 digit is enough. Don't worry. 2 or 3. If system it take a 3 digit, and provide a 3 digit also.
Sir, can you please summarize this particular assignment? Some of us might have joined little bit late.
Which one number questions, please?
From serial number 1.
Cell number 1 to
Yes.
10.
Just
Sir, example 4 and 5. Explain again 4 and 5 example. Question number 4 and 5.
Sir, one doubt in the last question, sir.
Yeah. Tell me.
So the DIF by dt
Yeah.
is the slope of the forward current, no? So,
Yeah.
like it is from IF to that 0.0, sir. It will be coming till IRM, the slope.
No. If you take this one from here to here,
Yes, sir.
then you take total time from here to here.
Okay.
Then this is on slope. If you take
Yes, sir.
IRM to 0, it means we will take only TA time. I have only TA. It is not mentioned about this one time period. That's I can take minus IRM to plus IF.
Okay. So the slope is from IF to IRM. The value given DIF by dt covers from the IF to IRM, sir. The red line fully.
Yeah. But slope, if you have a slope like that,
Yes, sir.
yes,
Yes, sir.
yeah, seen like that. If you have slope like that, then you take any value of this one from this one. You can take this one and this one. Find the slope.
Okay, sir, understood. But the
delta y by delta
DIF
x. Yeah.
the DIF by dt, that rate of that forward current change in the forward current will cover till that IRM. I'm asking, sir.
Yeah, this one of forward current is slope. This one from here to here is the same slope.
Oh.
DIF and IRM is the same slope.
Okay.
Not changes. Then you can use the same slope for both.
Oh, for both reverse and forward current, the same slope.
Yeah. Yeah.
Sir, can you
Tomorrow,
explain question?
Question
tomorrow is
number.
also
Hello.
your session, sir.
No, next week same timing.
Then it will cross the 8th of February.
Okay, I think I don't know about your assignment. That's why this one is some mistake.
Sir, can you explain question number 4 and 5 again?
Okay. I explain. This one question number 4, na? A circuit diode given current carrying a 5 ampere with a forward voltage drop of 0.4 volt is used in a forward converter. In power converter. If the diode has junction ambient thermal resistance, junction ambient, this is from junction to ambient. This is the graph of the mounting of any devices. The junction temperature. Junction temperature means where PN junction is provided, and after that the cases of the devices and sink for the next session on 6th. No, I think Friday same.
Monday,
Seven-
sir. Sir, Monday.
No, I have a Friday session, not a Monday. Monday I have some other TA, I think. I think this is second TA. Don't worry. I have some another TA on the same topic. They provide you. They will provide you. Don't worry. They have junction temperature and case temperature in sink. Sink is where the places heat sink, and ambient temperature is the outside of the devices. And given is the voltage drop and forward current. Simply find the power of total power is the same in thermal cases and electrical cases. You use the same power and energy is the same, mechanical and thermal, electrical, all of them, but the notation of the voltage and current is different. Here the given the junction with ambient thermal resistance is given from here to here. Is a 40 degrees centigrade per watt. Okay, then simply apply Tj to Ta, this one junction temperature to ambient temperature, heat flow like that, this one junction to the outside there, and total power, and then find the Tj, junction temperature. Power is given 2.5 bar, RT is 40 degrees centigrade, and Ta also given 40 degrees centigrade. Use of this and find the junction temperature. Is okay?
Okay, sir. Then question 5 also, sir.
Okay. Same thing applying question number 5. Question number 5 is given reference to question number 4. It means power is the same, and ambient temperature also same, because of is here not given another ambient temperature. That's why you will take the same ambient temperature in question number 4 and question number 5. In question number 4 is given ambient temperature of 40 degree centigrade. Okay. Then Tj minus Ta divided by total resistance, thermal resistance, is equal to power. Same thing, Tj is given 100 degree centigrade. It given, and Ta is at 40 degree centigrade, and the power is same 2.5 watt. And RTH is a combine all of things, TJC, RJC, and RCS and RSA. We had all of the resistance in series. Then find the thermal resistance of SA. It's asked about the sink to case to sink. sorry, it asks about the thermal conduction of heat sink to ambient. This one. If you are to have a series, all of the 24 thermal resistance RTS overall RTS, and then find RTS is 24 minus given RTS JC and CS, the 11 degree centigrade per watt. It's okay.
Okay, sir, understood.
Sir, next
Sir,
session will be from another TA.
Yeah.
That is on Monday and Tuesday, both days.
Yeah. I think we have a 3 TA for your this topic, this subject, fundamental of poly electronics.
Okay.
We are 3 TA.
But they are covering different topics.
I think yes, yeah, some same topic or some different topic also.
Because next on Monday it will be on next on BJT or like that. I think so.
Okay, they will talk about that. They will
Okay.
sir, can you share this PDF or can you upload on YouTube?
This one, yeah, I upload this one on YouTube.
Today, tomorrow.
I think today nights or tomorrow.
Okay, thank you, sir.
Thank you, sir.
Okay.
Sir, just to say maximum temperature is 100, not 120, sir.
No, 120 is the maximum operating temperature of any devices, but
Okay.
devices operate on 100 degree centigrade.
Oh, junction temperature is 100. Okay.
Yeah, it operate at 100 temperature, but it have a maximum operating temperature of 120 degree centigrade.
Okay, sir.
Yeah, it's given a maximum temperature. It can operate, but it operate on 100
It is operating at 100 degrees.
Yeah.
That 40 from where, sir?
What is?
TA where?
Sorry?
The ambient temperature is referring to question 4. Okay, sir.
Yeah, given referring to question number 4.
No, the question 4.
Which one data is not given in question number 5, then you can
We'll
take
refer
from
to
the
question.
Yeah.
Okay, sir. Thanks.
Any other questions, doubts?
Sir, that duty cycle problem, no, sir.
Duty cycles, I think question.
You're calculating that power dissipation of the diode. Yes, sir, this one. Yes, sir. This one, if it could have been play, instead of a square wave, it is a DC voltage.
Yeah.
Directly, we can multiply I into RD plus ID into IL into VD, sir.
You can apply, if you find a I average and I RMS, then you can simply multiply.
No, instead of a square wave,
Yeah.
input given here a square wave. Instead of the square wave, when a DC voltage is given, constant DC.
Yeah, you can simply apply this. Don't wait.
Just
Then
we can divide that
ratio-
voltage by current and directly I into RD plus that load current into diode voltage VD. That is sufficient.
yeah,
No?
like a question number this one. Question number 6 one.
Okay, like that is you can do it.
Here not mention the square can mention and not mention the duty ratio. Then take out 40 is the value.
Okay, 40 by 20 is the IL.
Yeah, this one the current.
Okay, that current into that IL into RD 50 milliohm.
IL into RD plus IL into VD.
That VD 0.6.
But IL square, don't take only IL. IL square because of power loss is the I square into R.
Oh, that is I square into RD. Okay.
Yeah.
Okay.
Chal, Dhaval.
Oh, yes, sir. I want to ask about the ambient temperature. Okay, so in previous question it is given 40 degree Celsius, right?
Yeah.
But as I have seen in data sheet that temperature range is between minus 65 to 150 degrees Celsius. So why do we consider ambient temperature? It means if I am given so much range of minus 65 to 150 degrees Celsius, right?
No, this
So
one is
why
a different diode. Diode part number is given there.
Okay.
Here is not given. Here is the Schottky diode. There is the fast recovery diode. Both are different.
Okay, sir. And okay, and another thing is that miss, for different miss region, we will have different ambient temperature, right? So
Yeah.
for each, so they either they don't have diode, means they have which miss like different ambient temperature for combined. For miss every different place they will have different ambient rating for in Arab, and there will be 60 degrees Celsius or something more,
Yeah.
50, 55. So in some other continents there will be lightly less. So for different ambient temperature we will have different diodes, or we don't have range for that particular thing.
No, you should have choose a diode for which one purpose you have choose and where you work on this, like the whether countries where you use like Arab countries or some other where. And if you then you choose like a diode, choose like a choose diode like this that season that the operating temperature. This one. This one is the ultra fast diode is given like that. Then you choose the check many type of diode and have many ranges of and of other diode.
There's a
Different
void
diode.
operating.
Sorry. For different diode have a different ranges of the temperature. If you have a use a diode for 100 degree centigrade, then choose that one diode, not this one diode. If you have a minus 60 degree centigrade, then use that type diode that you use for 60 degree only, minus 60 degree ranges of something.
Sir, if that is the case,
Yeah.
if we have if we have buy a module of a buck converter for some application with a
Yeah.
current limiting circuit.
Yeah.
So if you if we use that buck converter, it like the buck converter is made such a way that it can operate in anywhere in our country. No, it is not either in Kashmir or in Tamil Nadu. It can able to operate. No, sir.
Yeah.
In that way only it has been done.
Yeah, that's why you provide a huge number of range, na minus
Yes, sir. Yes, sir. It has a
65
wide
to
operating range.
yeah minus
Then
65 to 150 degrees centigrade. It's a
yes,
huge
yes. Yes, sir. In
temperature.
that case, like we don't have such an different thoughts of usage of different diodes in different places.
No. If you have at that places you have a specified temperature like minus
Yes, minus 65 to
minus 0 degree or minus something minus 10 degree like that.
yes,
Yeah,
yes, sir.
200 degree, more than 200 degree, yeah, more than 300 degree. If you have some very places, that
Yes.
places you have a different diode.
Okay.
Yeah, in that
In that
places
case,
you
buck
can't use
converter
this.
built here cannot be
Yeah.
used in that area.
No, but 100 degree or 150 degree temperature is very huge temperature. You
Yes.
for any converter, then it is normally used like minus 65 to 150 is enough to anywhere you can use.
Okay, sir. Thank you, sir.
For a special purpose you can use. You can search for a special purpose.
Okay, thank you, sir.
Okay. Any other questions?
Thank you, sir.
Okay, I provide you a link NPTEL. I will provide you a link in next session. It's okay for you? Hello?
Okay, sir.
Okay, sir. Okay.
When I will uploaded the video, after that you provide you a link for the channels.
Hello.
Yeah.
Sir, please repeat the question number 9.
This one. What is the doubt?
Oh, sorry. Question number 10.
Yeah, this one.
Ji.
What is doubt?
Sir, actually, we have taken some data from data sheet of the diode.
Yeah,
Uh,
from data sheet you take a TA value from there.
okay.
Here is not mention any TA value na, TA time. What is the time to take a reverse maximum current? Is not mentioned here. If you see a data sheet, I will see this one.
Uh,
This one is given TA time here in data sheet. Is a 30 nanosecond. Take a TA value from here.
and sir, I am solving a question number 5, in which theta SA.
Question number 5. Yeah.
So actually, when I was solved, my answer is 13.33.
13.33.
Ji.
What is take you have take ambient temperature.
So I take sink to ambient temperature.
No, ambient temperature. Sink to ambient is the thermal resistance, not a temperature. Ambient temperature
Sir,
is different.
ambient temperature is 40 degrees Celsius.
Yeah, this okay.
And junction temperature is 140 degrees Celsius.
Junction temperature take 100 degrees centigrade, not 120 degrees centigrade.
No, sir, I take a 140 degrees Celsius.
140.
Yeah.
Why? See here mentioned the temperature calculated is outside the maximum operating range. Maximum operating range is given 120 degrees centigrade, but it operates on the 100 degrees centigrade, not 120 degrees centigrade or 140 degrees centigrade.
Sorry, sir. Sorry.
Yeah.
Sorry.
Any other doubts?
Answer question number 7. 1 point.
Yeah.
Sir, in question number 7, my answer is 1.372.
Power 1.
372. Oh, sorry, sir.
What is the RMS value and average value of current?
Sorry, sir, but actually I directly calculate ID into VF.
ID into
VF.
no.
Average current into forward voltage of the diode.
No. Take RMS resistance also present in the diode, na? Then power loss also and resistance. So take both resistance power loss and forward voltage drop power loss.
Okay, sorry, sir.
Yeah.
Thank you, sir.
Okay, welcome. Any other doubts? Anyone?
So please upload this video on NPTEL login page.
Yeah. They will provide you a link.
Okay, sir. Thank you.
And I have also provided. I will also provide in the next session. When I will upload this video on YouTube, I will provide you a link.
Okay, sir. Thank you.
Yeah, Dhaval, any other doubt?
In that question number question number 5, sir. Okay, so we have different junction from theta. Okay, from junction to K sink, from sink to ambient. Okay, sir.
Yeah.
So we are minusing junction to case and case to heat sink, and that the value which we got are theta, right, sir? So we are getting 11.
Yeah.
So why are we calculating different R theta junction and this one?
Because I have given
junction to case.
Different thermal resistance is given na, from here to here. From junction to case is given different temperature thermal resistance, and the case to sink is given a different thermal resistance. Then ask about the sink to ambient, what is the thermal resistance?
It means that power loss happening for particular case, right, sir?
Yeah.
Particular this to this. So we are calculating total power, and so we will calculate the heat sink accordingly, right, sir?
Yeah.
So how much means total power? So getting, so I'm total heat to ambient. So I'm getting 11 degrees Celsius per watt. So
Yeah.
means per 11 per watt I'm getting 11 degrees Celsius the power loss, right, sir?
Yeah, this one for the surface to ambient temperature.
Surface to.
It
So
will take
for total, if I have to, I've given that particular diode, so I have to design the whole system. So I have to calculate all three components and add it. So
Yeah.
that total power will be per degree Celsius of more than that. I should select the heat sink, right, sir?
Yeah,
For that.
yeah, you can do.
Sir, how much means if I'm getting example 50 degrees something, right? 50 degree per watt. So should I buy 70, 80, or what's the range? What's the thumb rule? Means twice, 1.5 times, or how should we decide the heat sink for particular with that one?
You can greater than this one. You can about 1/5 or twice.
1.5 or twice, right?
I mean.
Okay. Thank you, sir.
Okay. Welcome. Okay, everyone. I stop here.
Yes, sir.
Okay. Thanks to all and good night.
Thank you. Thank you so much, sir.
Thank you, sir.